So stochastic control is a huge subject, and I will sort of build up to it. But as a cartoon, this is the picture that I want you to have in mind. There's a complicated system, and we have indications about its state, but we can't observe the state directly. And we also have actions that we can take by turning knobs. And each of these actions jiggles the state of the system, not by very much. And what we're hoping to do is we're going to try to achieve, to bring the system to an acceptable state. And the general idea is that the set of acceptable states is an exponentially small fraction of the entire state space. So it's not an easy thing to do, and our goal is to drive the system in that direction. So a realistic example of stochastic control would be something like this. But this is a theory talk, so we'll simplify things a lot. So I will start from somewhere that seems relatively far away. I will start with the so-called Lovász local lemma and the probabilistic method. So in the probabilistic method, what we do is we want to exhibit that objects with certain good properties exist. In this case, for us, in the background of our heads is the idea of states that we're happy with. And in order to demonstrate that these objects exist, we place a probability distribution over a state space and then argue that the desirable states have non-zero probability. And desirability is typically framed by defining a collection of bad things that can happen, things that can go wrong. And a state is good if in that state none of the bad things is happening. So you have a probability, this is just pure probability, you have a probability space, you have a collection of bad events. And then obviously, if the events were independent, then the probability that no bad event occurs is simply the product of the complements of the probabilities of the bad events. And this is always strictly positive as long as no bad event is deterministic. The problem is that in the vast majority of interesting scenarios, the bad events are not independent from one another. And in particular, you're in a situation in which avoiding one bad event increases the probability of some other bad event. It boosts it. So let me give you an example. Imagine I wanted to prove to you that this formula is satisfiable. And the way to do it would be to look at the binary cube. There's 3 variables. So I'll take the uniform measure on the cube. And then I will try to prove that, there is some truth assignment is satisfying. So a satisfying assignment has non-zero probability. So if I define my events to correspond to the violations of the clauses, then this event over the uniform measure of violation has probability 1/4. The problem is, if I expose to you that this clause is happy, this biases variable x2, it makes it a bit more likely that it is 1, which suggests then that this clause is less likely to be happy. Another way to think about this is if you sort of think geometrically. If you think of the volume of your probability space, you have your different events. If the events are independent, then their intersections must have size exactly proportional to the product of the events. But if events are dependent, then they are allowed to be repulsive with respect to one another, and therefore in aggregate occupy even more volume, potentially covering the entire space. So you can interpret the Lovász local lemma as saying that in the presence of limited amounts of dependence, you can still prove that the union of the bad events doesn't occupy the entire probability space. And the simplest formulation of the lemma says the following. Assume that every bad event has probability at most p, and moreover, it is independent of all other events except for up to delta other bad events. Then if p times delta is less than 1 over Euler's constant, then the probability that nothing bad happens is strictly positive. Clear? So one of the nicest applications of the Lovász local lemma is to show that every KCNF formula in which each clause shares variables with at most 2 to the k over e other clauses is satisfiable. And the proof is very straightforward. We just say, take the uniform measure over the probability space, so over the binary cube, so over the 2 to the n possible assignments, and observe that under the uniform measure, each clause is violated with probability 2 to the minus k. Moreover, if I tell you this, some clause is satisfied or violated, and this clause doesn't share variables with some other clause, then obviously this exposes no information about this other clause. Therefore, in the local lemma sense, the number of clauses with which you share variables is an upper bound on the number of other bad events with which you may not be independent. So what you need is that P times delta is less than 1 over E. So P is 2 to the minus K, which implies that delta can be as high as 2 to the K over E. Okay. Now, in spite of the fact that this was incredibly effortless, it also turns out to be tight. And proving that statement is far harder. Okay? But it should give you some idea that the Lovász local lemma is not a toy. Okay? It can actually get to the edge. If the only thing that you know about your formula structurally is the number of intersection, it actually takes you to the sort of to the edge of reality. So now, after you know that satisfying assignments exist, or more generally, after you have demonstrated that the objects that you want exist, the next question is how to find them. And there was after the Lovász local lemma started, dominating probabilistic combinatorics, there was a lot of effort to make it constructive, meaning to come up with an algorithm which will, in polynomial time, actually find an object, find an element of the probability space that simultaneously avoids all bad events. And there was a sequence of papers. The conditions, though, required were significantly more stringent than what the existential lemma requires. And then in 2009, Robin Moser had a breakthrough in which he showed that, at least for the problem of satisfiability, you could get delta to be pretty much right, except up to, to a polynomial factor. And moreover, it turns out that Moser's ideas, if you're a little bit more careful, get you exactly what is reality. So in polynomial time, you can find a satisfying assignment under this condition. And what is perhaps even more remarkable is the simplicity of Moser's algorithm. So this is a 3CNF, except that when a light bulb is lit, it means that the clause is unhappy. Okay, that's why it's red. So if it is silent, it means that the clause is happy. And blue versus that color is whether the light bulb wants the switch to be 0 or 1. So Moser's algorithm sets start at an arbitrary configuration of the switches, and then in every round, just pick uniformly at random an unhappy clause, a lit light bulb. And then without looking at the current state, just rejiggle the switches that correspond to the unhappy light bulb. So in this particular example, let's say I would pick this one, and then I won't even look at what these are set at. I'll just reinstantiate the 3 variables corresponding to this clause with equal probability 50-50. And then the theorem is that, in fact, in linear time, linear in the number of variables and the number of clauses, this will find a satisfying assignment under the condition of the Lovász local lemma. So in joint work with Fotis Iliopoulos, we sort of tried to introduce a generalization that would allow you to apply similar ideas in a broader concept, and we developed what we call the flows action framework. So we take omega is a big arbitrary set, so this is our state space. So this is the equivalent of our probability space, except I haven't talked about probabilities yet. And then we have subsets that we call flows. So when a state is in here, it means it sort of suffers from this law. We group together states according to some particular deficit that they have. And our question of interest is whether there exist states that escape the union of the flows that we call flawless. And the general idea is that if such states exist, we would like to discover them in time which is significantly smaller than the size of omega. Okay? And the plan for doing it is we're going to implicitly specify a directed graph on the entire state space such that every flawed object has out degree at least 1. So if you're in a bad place, there's somewhere to go. On the other hand, every flawed object is a sink, so you're happy there. And we're going to start at an arbitrary state, so it's enough to get any kind of foothold into the state space. And then from there, we will take a random walk until we reach a flawless object, until we reach a sink. That's the general plan. More concretely, the way that we will implement the plan is, if this is our current state, let's say sigma, we are going to look at the flaws that are present in the state. So sigma suffers from flaw 1 and flaw 3. And we're going to select one of those flaws at random. And we will try to jump out of it. We will try to escape. And the way we will try to escape is sort of the obvious one. We're going to have some transitions. Hopefully most of them will take outside the flow. But some of us might actually keep us inside the flow. Okay? That's the general idea. So for any flawed state, for every flaw present in the state, you have some choice of actions that you can take over a probability distribution. And the overall algorithm is, whenever you're in a flawed state, pick one of the flaws uniformly at random and just try to fix it. Okay? And then the question is, will this ever converge? Because obviously when you try to fix something, you might break something else. Are there any questions up to here?
Where do the probabilities come from?
I haven't said anything yet. Yeah. I just wanted to make sure that these numbers add up to 1. That's the only thing, yes? All right. So just as an example to keep in the back of your head, if we have a KCNF formula with n variables and m clauses, our big space is the binary cube. The flaws corresponds to the clauses in the sense that they are the subcubes that violate each of the clauses. So F1 is all the states in which clause 1 is violated. And then the arcs or actions for addressing flaw I at a given state, remember that a flaw corresponds to a clause, are all the possible 2 to the k mutations of that particular clause. So when I said you can rejiggle the variables of that clause, there's 2 to the k possible ways of doing it. And then finally, the probabilities to ask Moshe's case, in that particular case, they're all equiprobable. So this is how Moser's algorithm will fit in the flaws actions framework. Okay. So now in order to get a theorem that says this will finish in a reasonable amount of time, I have to sort of become a little bit quantitative. And there is a few quantities that I need to discuss, but not many. So let rho sub I sigma tau denote the probability that I will go from state sigma to state tau when addressing flaw I at state sigma. So I am at, let's say, some particular truth assignment, clause I is violated. What's the probability that I will go to state tau? Okay? So this probability distribution at a particular state has some entropy. And so this is the entropy of the probability distribution for addressing flaw I at state sigma. It is just the entropy of those 3 arcs that I said. And now I'm going to take the minimum of this over all the states in the flow. So what essentially this is saying is, when my state suffers from flaw I, how much entropy, at least, will I inject into the system in my effort to perform state space exploration?
These are uniform, right? They're all the same.
No. In general, this is an arbitrary probability distribution.
No, but for the previous example.
That's right, for the previous example.
They're all the same, right?
Yes.
It's a uniform distribution for every sigma. Okay. Yeah.
Yes?
Yeah.
All right.
Read the next.
It was even on the same slide. So is it clear? So I want this quantity to be big, right? Because if this quantity is big, it sort of suggests that my actions tend to explore the state space because they have to go to many, many different places. There's lots of destinations, and I sort of visit all of them with reasonable probability. So I want the local entropy of each flow to be a large quantity. Now, that in and of itself is not enough, because in principle, you could imagine that all the different actions for getting out of a particular state end up going to the same place. So for example, here, this is a state in which I have a chance of getting to both from here and from here. So if all of the outgoing arcs, in some sense, were contained in a tiny part of the state space, this would create congestion. Okay? So I want to avoid congestion. So on one hand, I want the image of this transformation to be uniform over the state space, to be large, so that I explore the state space. But I don't want there to be collision so that it is genuinely large. And because I want to have a local characterization of what this means, the way that I'm going to talk about congestion is sort of rather brute. Specifically, we're going to define this quantity. We're going to say, take an arbitrary state tau, not necessarily in a specific flow or not, and look at the number of states for which this is a possibility in flow I. In other words, when I'm addressing flow I, from how many different states of that flow may I end up in tau? So this is basically just the in degree. So this has in degree 1, this has in degree 2. And because we want to eventually compare this with an entropy, we're just going to measure this in a logarithmic scale. And then finally, because we want a local characterization, we're going to take the maximum over omega. Okay?
So you do not weight it by what's the probability that you go from
No.
here?
No, and that's part of the entropic part in the title of the talk. It's just going to be counting. Yes?
It could be very, very tiny, right? But yet you're still giving it
Yes. In general, this sort of doesn't typically happen in applications, more or less, I will say. Okay, but I mean, your question is well posed, right? Is a meaningful question, but I won't deal with this. I just deal with this in this sense. And in particular, I claim that the congestion of every flow in Mosel's algorithm is 0. And the reason this is 0 and not 1 is, remember, we're taking a logarithm. So essentially what I'm saying is that if this is a violated clause, and I look at all the outgoing arcs, there are never collisions. And the reason to see this is, imagine this is a state, and I told you I arrived at that state because I fixed a specific clause. Well, that clause was violated in the previous state, and there's only one way for a clause to be violated, by the nature of satisfiability. Okay? In general, the congestion is what it is. Okay, so those two quantities, local entropy on one hand, and lack of congestion on the other, I can combine them to define a quantity that I call the amenability of a flow. So the amenability is a positive word. You want this quantity to be big. So it's the local entropy as defined minus the congestion as defined. And this is, I'm just reiterating what I had in previous slides. So for any particular flow, I look at all the arcs leaving the flow along with the associated probabilities. And this allows me to define what the amenability of the flow is. So amenability is good because it suggests search space exploration at a rapid pace. Big amenability. Now, of course, achieving big amenability on its own is kind of trivial. Because what I could do is I could just literally reset all the variables in every step. Okay, then, this would basically just be going everywhere. So in reality, I want it to be the case that on one hand, I explore the state space, and I typically get out of the bad set that I try to address. But at the same time, I don't break too many other things. I don't introduce too many flaws into the system. And to measure that, we are going to introduce the other quantity that we need to measure, which I'll call potential causality. So this is a state sigma. This is the same probability distribution as in the previous slide. So to talk about causality, actually, we're not going to look at the numbers. We're just going to look at every arc for which the number is non-zero. As long as it is a positive probability, it counts the same. So this is the overall picture. I am in state sigma. These are the possible actions. And I will say that a particular choice of next state when addressing flow I at state sigma introduces, so we're put in this set, every flow that is present in the new state that was not present in the original state. Well, that makes a lot of sense. And we also put the flow itself if we failed to escape from the set. So gamma sub I sigma tau is I was at sigma. I decided to address flow I. I ended up in state tau. In state tau, what flows are present that were not present in sigma, A, and B, did I manage to escape, flow I, the original state in which I was? That's my set. So, for example, in this case, this arc takes us to this state, and the only relevant state is here. So we introduced flow 4 if we do this. On the other hand, if we look at this arc, this new state belongs both in flow 3 and in flow 4, but observe that flow 3 was already present in the existing state. So this transition only introduces flow 4. It doesn't introduce both 3 and 4. And then finally, this transition introduces flow 1 in the sense that it reintroduces flow 1. So overall, this particular state, moving away from it, has the potential to cause flows 4 and flow 1. Okay? And then, again, because I want to have a local characterization, I'm simply going to define the neighborhood of a flow to be the union of everything that can be broken whenever I decide to address that flow in a state of the flow. So it is the union over all states in the flow, over all the actions I can possibly take on those states of what may possibly be introduced. Okay? So in Moser's algorithm, again, sort of our guiding example, observe that each clause can potentially cause another clause only if they share a variable. Okay, if they don't share a variable, you cannot cause that other clause to happen. Moreover, you have to disagree on that variable. If you agree on that variable, again, you can't cause it to happen. If it was unhappy before, it wasn't due to you. It's not going to be due to you in your new state. Either you'll be happy together or you'll both be unhappy. And then finally, because I said that each of the 2 to the k possibilities has equal probability, this also includes the self-loop state. So there's a 2 to the minus k probability that you stay put. Therefore, every clause has the potential to cause itself. Okay? Are there any questions? Okay. So the general scheme then is we have such system of flows and actions. We start at an arbitrary state. And then what we keep doing is we say, let f sub I be a random flow present in the current state. Okay, among the actions available for addressing the chosen flow in the current state, pick one according to the prescribed probability distribution. I'm just rewriting this notion of how we walk in the state space. And then the theorem is that if this inequality holds for every flow, then there exists some critical time such that you will walk for about that long, and after that point you'll have a cutoff phenomenon. The probability you won't reach a sink s steps after you've walked the cutoff time decays exponentially in s. So it's not just polynomial time convergence, but it's more like you will walk for a while and then boom, the probability drops very, very rapidly. And then what you sum over here on the left-hand side is 2 to the minus amenability of the flows that you may cause. Okay? So flow I burdens the system in relation to the flows that it may cause. And in particular, the flows that it may cause are burdensome by 2 to the minus their amenability. So a highly amenable flow is not a big deal, doesn't contribute much to this sum. The point is, this is a relatively easy quantity to compute because the criterion is local. And if we plug this into our sort of running example, observe that the amenability of each clause in Moser's algorithm is k, because you use k random bits in every step. That's the entropy of the probability distribution. The congestion is 0 because we took a logarithm. So this is k. So this inner term is 2 to the minus k for every flow. So you can afford to have up to 2 to the k minus 2 so that this is less than a quarter. So we match the result, except that instead of having 2 to the k divided by e, you get 2 to the k divided by 4. But the difference is I don't have variables. This can be a very complicated space. There's sort of several advantages to this formulation. Is there any question? Yes.
Do you have anything on the other direction? I mean, if that sum is too large, can you argue that it?
You mean like a negative result?
Yeah.
Well, I don't want to go into too much, but actually, in a certain way, we can make this become over E as well. In which case, the same counterexample, the one that corresponds to CNS, works for both problems. Okay? So this was all actually past work. It wasn't the work that I'm sort of really talking about. This was just to set things up. And the work that I want to talk about today stems from this observation. So this is Moser's algorithm. And observe that it has the following delightful property. You don't have to know the state to run the algorithm. Okay? Someone can be hiding behind here. They choose the initial state. Okay? And then they just do the coin flipping for you. Is this clear? All that they're doing is they're telling you which light bulbs are on, and then you just rejiggle them. Observe that, for example, from this picture, you know very, very little about the current state. Maybe you know things about the variables corresponding to this light bulb, and the things about the 3 variables corresponding to that light bulb, and these, but there's a ton of things that you actually don't know. Okay? So this is an algorithm that manages to work while it has a very, very gentle relationship with the state. The only thing that it needs to know is this macroscopic feature of which flaws are present in the state and which flaws are not present in the state, and it'll still work. So this raises the question of what happens if the agent that is actually sort of acting inside the state on our behalf is imperfect, in the sense that, for example, the light bulbs are faulty, meaning sometimes a light bulb that should be on is not on, and the light bulb is on when it's actually off. Also, what happens when we flip the coin, and that coin flip corresponded to actually switching a variable from 0 to 1, except our command doesn't get executed. And finally, imagine that this agent running inside here also has a bit of a mind of their own, so they're injecting noise into the state. Okay, so that the state drifts away from our actions. So not only do our actions not always happen, not only do our actions suffer from the possibility of being misguided, but in fact, there is also internal drift in the state. So the question is, can you still hope to find a satisfying assignment under these conditions? And the reason I'm giving the talk is because the answer is yes. And the sense in which the answer is yes is, if we go back to this inequality, when this inequality holds, it holds with some slack. Okay? So the point is, I can take this slack, which you can interpret as lack of internal conflict in the system. So when this quantity is small, right, my system moves rapidly to a good state. So I can take this lack of internal conflict and turn it into noise resistance. So the more slack you have in your formula with respect to the original criteria, the more noise I will be able to inject. And the way that I will sort of talk about noise injection is very general. So let's look at a specific flow. So this is flow 1. And these were the transitions under our good algorithm. This is what we wanted to happen, and we had numbers on these. Okay? Now imagine that the adversary comes up, and they set up their own collection of arcs. Some of these arcs are arcs that we used to have, but they can also put in arcs that didn't exist at all. And moreover, they can put their own probability distribution on these arcs, whatever they want. And it takes a little bit of thinking, but it's not hard to see that if you give the adversary this much power, this is enough to simulate all of the 3 different things that can go wrong that I said in the previous slide. Okay? So this is the setting. So this is how we're going to model noise. And overall, we're going to say that state evolution occurs as follows. In every step, with probability 1 minus p, the system acts normally. And with probability p, the system acts according to the adversary's wishes. That's it. That's my model of noise. So in every time I take an action, either the system will behave as it's supposed to, and that happens with probability 1 minus p, or the system will act according to this, in some sense, anti-algorithm imposed by the adversary that tries to keep me from reaching a good state. Yes?
So we can put any probabilities on the arcs.
Yes.
On any
This graph is completely arbitrary. Of course, I will quantify the nastiness of this graph in the next slide, right? That's the point. And then, of course, also the value of p will be a big deal, yes? The nice thing, I think, is that I can do this in a uniform manner, by which I mean that you can think of the adversary's chain as an algorithm exactly like my algorithm. And you can go on and compute the same quantities like local entropy and congestion and all that, yes? So in particular, you can say, under the adversary's actions, what flaws, so this is star for adversary action. So what flaws can be introduced when we try to move away from state I? And moreover, what is the worst case congestion over all flaws according to the adversary's algorithm? And now I have this expression, which is a little bit complicated because I want it to be sharp, but it's easy to see that the dominant term is the probability that we move according to adversary action, the number of flaws that can be introduced by the adversary that sort of I wouldn't have introduced, and then finally the worst case congestion that the adversary can induce in their own chain. So this gives you a quantity. And then the theorem is that you get this quantity to show up here. So when p is 0, in the noiseless case, this quantity is 0. So I just recover the original result. And the more slack you give me in your standard algorithm, in some sense the fastest the system would have converged unperturbed, the more noise it can tolerate and still converge.
Dimitri, I'm a little bit confused about the earlier version of this result, but I think I can ask my question on this slide.
We have 5 minutes, so we have plenty of time. I'm done. So this is next slide.
Basically, so gamma does not appear in your original version of the theorem.
Doesn't?
My puzzle is where do you? Oh, this gamma.
Okay. So I am a flaw, and I want to make sure that in some sense I play nice with respect to the system. Okay? What does it mean? So the theorem says if every flaw plays nice. Now, what does it mean for a flaw to play nice? We look at the flaws that may be introduced into the state in taking actions to get out of flaw I. Okay? And then we look at each one of those flaws. How amenable is it? And the more amenable it is, the less it counts towards the burden that we impose on the system. So no, the gamma is still there. Yes.
I feel that it should still be weighted by, this should be a weighted sum rather than this, because of how certain actions are taken with very low probability you'll land in something else, right?
Yes. So this is a correct intuition. This is a correct intuition. But it is hard to get away from this being a hard notion. Okay? So at least later when we introduce this noise aspect, observe that we succeed in making this a soft notion in that the adversary can make this very big if p is sufficiently small. In other words, the typical sort of the defining feature of the Lovász local lemma is a certain notion of sparsity of dependencies. Yes? So for the first result I spoke, you want that sparsity of dependencies. And now I'm just going to, on top of that, pile an ugly layer. Yes? And what's nice is that I don't need the ugly layer to be sparse if it doesn't have very high intensity.
There's a question.
How difficult is it to discover a structure like this? Like the transition structure that will give me the good T0?
I mean, this is just generic. I have no answer. This is generic algorithm design.
But But surely the complexity of the problem, it will depend on how easy it is to construct this thing, up front.
I mean, one way to think about all this is what we're doing here is sort of focused stochastic local search, right? We have a collection of constraints. We need to satisfy all of them. In every step, we pick one, and we try to make it happy. Yes? Now, there's an entire art about choosing among the possibilities for making it happy. So, like, to give you an example, if you look at, again, at satisfiability, you can say, I'm going to pick a violated clause. And let's say if it has k variables, I'm going to pick one of the k variables and flip it. Okay? This will guarantee that this that this particular clause will get fixed. Of course, it might break other things. How should I pick a variable? Here's a reasonable thought. You could say, variable 1, if I flip it, it fixes 5 things, it breaks 3 things. If I flip variable 2, I fix 2 things, I break 4 things, and so on and 4 things. So these two numbers, what you fix is typically called make, and what you break is typically called break, okay? And then, if you want to think a little bit sort of like a statistical physicist, a very natural probability distribution to use for selecting which variable to pick is e to the minus beta. Beta is a positive number, make minus break. So, you think about the energy of the system, okay? Guess what? It turns out there is something much better than this, which is this. This is a highly surprising fact, okay? On the other hand, it is somewhat parallel with what I'm saying here, because observe that I never talked about what you fixed when you moved, okay? So at best, what I talked about can be thought of as perhaps giving some guidance that is quantitative on how to make local selection rules. Although, to be completely honest, I don't know if it has practical value. It is good for proving theorems in the sense you can prove things in probabilistic combinatorics. Okay? But my intuition is that in real life instances, you can make better choices than the choices that optimize the criteria that I said. Nevertheless, I find it somewhat satisfying that the theoretical criteria are sort of consistent with the removal of this term.
So I have another question. There are 2 words that I don't understand in the title. Control and compression.
Okay, yeah. So the truth is this was the first half of the talk. Okay, so I just talked about stochastic control. I didn't talk at all about entropy compression. I can take 1 minute perhaps to talk about that. It's still, I think I have 40 minutes. I think I have 1 minute left. And I've been answering questions, yes? Yeah. All right. So imagine that you give me a formula and I'm supposed to execute Moser's algorithm, okay? And we're going to have a deal. I'm going to try 1,000 steps. If I don't find a satisfying assignment after those 1,000 steps, I stop. Okay? We both know the formula. But now I'm going to execute the algorithm inside this room, and you're going to be sitting outside. And you don't see my random bits. All you do is you hear me sing which clause I am actually dealing with in each step. Okay? Clear? All right. So now fix some particular sequence of clauses. Clause 25, followed by clause 42, followed by clause 17, and so on and forth. 1,000 in total, yes? What is the probability this is the song you will hear? I claim this probability is at most 2 to the minus t, so 2 to the minus, sorry, k if it's a KCNF, to the 1,000. And the reason is, if we fix this a priori, and let's say I pick my initial state uniformly at random, the probability that this is violated is 2 to the minus k. But then I refresh all the bits. Yes? So the probability that this will be violated in the new state is also at most 2 to the minus k. And this gives me this. Therefore, what I have to do to prove that I win is to show that the rate of growth of the set of possible songs of length t is gamma to the t for some gamma strictly less than 2 to the k. If I can show that there are fewer than that many songs, then I just take the union bound and I win, okay? And here is the part that is sort of technically involved. Here is the interesting part. In principle, you could say, hold on a second, in any particular step, you could be saying any one of the many, 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 many clauses in the system. How are you going to get this base to be as small as 2 to the k? And the answer to this is that these songs are sort of not arbitrary. They're highly compressible. And the reason they are compressible is the following, and with this I finish. Look at a particular instance of a clause inside the song. Yes? Except for the very first one. The very first one we can attribute to initial sin, to the original state. Yes? But every subsequent occurrence of that clause in the sequence is the result of some transition in which this clause was happy and someone broke it. Yes? So there is a causal relationship going backward. And now the sparsity of my formula is reflected in the sparsity of the causal relationship. This compresses the songs. This gives me a growth rate less than something. And then by this argument, I get to prove that eventually things converge.
Okay, so let's thank the speaker and 4 o'clock. So we'll be back at 4.